Calling all Umis! Team Umizoomi!
1, 2, 3, 4. Billy, Gio,
Boss.
and you.
Oh no, we have a big problem! Mili, we have a big problem! What? The permutation monster has appeared! And boat is missing! Have you found boat? Where's boat, bro?
Shut up! We are the fine dining restaurant, right? So let's leave our squatter behavior outside!
What are you saying? Mili, we are inside our house! What are you saying? Are you stupid? Have you lost your mind?
Shut up! We are a fine dining restaurant right now. So leave your squatter behavior outside!
What are you saying? We are inside your room! Are you stupid? Have you lost your mind, huh?
I'm sorry, okay? I'm also panicking. Hey, you there! Can you help us find bot? Please help us defeat the permutation monsters!
To defeat the permutation monster, first, we must solve permutation problems to gather letters for a magic word. And once we say out the word, the permutation monster will disappear.
Are you ready to join us? Let's go! First, what is permutation? In mathematics, a permutation is an arrangement of objects in a specific order. For example, the different ways to arrange three letters are permutations. In everyday terms, a permutation is a way to reorganize or rearrange a set of items or elements in different sequences.
There are three types of permutation. First is the permutation of n objects taken R at a time. It is the default permutation, which is a linear arrangement of objects in a specific order where the order of the objects is very important. Secondly is the permutation of identical objects. A permutation of identical objects is a way of ordering a set of objects when some of the objects are the same. Lastly is the circular permutation. A circular permutation is the number of ways to arrange a set of objects in a circle when the order of the object matters. In a circular permutation, there is no beginning or end.
For the formulas, permutation of n objects taken R at a time uses the formula NPR equals n factorial over n minus r factorial, wherein n represents the total number of objects that are present in a set and r represents the number of selected objects arranged in a certain order.
The formula for the permutation of identical objects is n factorial divided by the product of n sub 1 factorial, n sub 2 factorial, and so on up to n sub k factorial, where n is the total number of objects being arranged, k is the total number of distinct groups of identical objects, and n sub 1 and n sub 2 and so on is the number of objects in each group of identical items.
The circular permutation uses the formula n minus 1 factorial. Oh no! The permutation monsters has locked the gate! We're trapped!
But wait, Millie, there's a clue here on the keypad. Look, the screen says, how many possible passcode arrangements can there be?
It also says that the first and last characters must be vowels. The buttons are labeled M, I, R, and A. Gio, what are the vowels?
That's easy. The vowels here are I and A, so the first and last positions must be I or A.
Right! So how many choices do we have for the first character?
Two choices, either I or A.
And what about the last character?
Also two choices, I or A.
Oh, I remember learning about permutations, Gio. Can't we use the formula NPR equals n factorial over n minus r factorial to solve this?
We can try, but let's think it through. The formula P of n taken r at a time is for arranging r objects from n total objects. But here we have restrictions. Only vowels can go to the last and first positions.
You're right! So instead of using the formula for all four buttons at once, we handle the restricted positions separately and apply the idea step by step. Okay, let's break it down using the formula for permutation. To solve and find the total number of arrangements, we will do 2p1 multiplied by 2p2 multiplied by 1p1, since no repetition is allowed. Let's break it down so it will be easier to understand. First, let's solve 2p1, which is equals to 2 factorial over 2 minus 1 factorial, and the answer will be... That's right! The answer is 2. Now, let's solve 2p2, which is equals to 2 factorial over 2 minus 2 factorial. And the answer will be... That's right! It's also 2. And for the last part, let's solve 1p1, which is equals to 1 factorial over 1 minus 1 factorial. So the answer will be... Correct! It's 1. And to find the final answer, we need to multiply the results together. So it will be 2 times 2 times 1, and the answer will be... Correct! It's 4. So we will get 4 possible passcode arrangements.
Wow! So even with restrictions, we still get 4 possible passcode arrangements.
That's so cool! Even though we didn't use the formula all at once, breaking it down step by step worked perfectly.
Oh, look at this! It says we need to arrange these blocks to form a bridge. There are 6 red, 2 yellow, and 4 blue blocks. But we have to follow these rules. The first block must be red. There must be exactly 2 consecutive blue blocks. No consecutive red blocks are allowed.
Let's first look at the blocks we have. 5 red blocks, 2 yellow blocks, and 4 blue blocks. That sounds tricky. How do we start?
Now, let us quickly review the conditions again. The first block must be red. 2 blocks must be consecutive somewhere along the arrangement. No more, no less. Red blocks cannot be placed next to each other. Now, we will solve the problem using the permutation formula for each case. But first, let us solve for the values that we will be substituting into the problem. To get the value, we will be using the formula n factorial over n minus r factorial, where n is the total number of items and r is the number of items being selected. For the case 1, we can assume that the blue blocks is placed on the second and third slots of the bridge. According to the condition, the first block must be red, and there are 5 red blocks. Therefore, we can represent it as 5p1. Next are the blue blocks. Since there are 2 slots and 4 blue blocks, we can represent it as 4p2. The next block can be either red or yellow block. Since we already used 1 red block, there will be 4 remaining red blocks, and we can add them to the yellow blocks, and we can represent it as 6p1. Lastly, the last color blocks must be yellow to satisfy the condition, and since we already used 1 yellow block, we can represent it as 1p1. This is represented as 5p1 times 4p2 times 6p1. Now, what is 5p1? And this pi p1 can be represented as pi factorial over 5 minus 1 factorial, which is equals to 5 times 4 factorial over 4 factorial, and 4 factorial will be cancelled, which leaves us with only 5. As for the 4p2, this can be represented as 4 factorial over 4 minus 2 factorial, which is equals to 4 times 3 times 2 factorial over 2 factorial, and the 2 factorial will be cancelled, which leaves us with 4 times 3, and 4 times 3 is equals to 12. And 6p1 is equals can be represented as 6 factorial over 6 minus 1 factorial, and this is equals to 6 times 5 factorial over 5 factorial, and the 5 factorial will be cancelled, which leaves us with 6 only. Now, we can substitute these values into 5p1 times 4p2 times 6p1, which is 5 times 12 times 6, which give us the answer 360. For the second and third case, it will yield to the same result. The only difference is the placement of the blue blocks. In the second case, the blue blocks may be placed on the third and fourth slots, while in the third case, the blue blocks is placed on the fourth and fifth slots of the bridge. We only need to solve one case, and whatever the result is, we need to double it. And we decided to answer case 2. Same as the first case, the first block must be red. Therefore, we represent it as 6p1. The next block are yellow block, and since there are 2 yellow blocks, we can represent it as 2p2. Next are the 2 consecutive blue blocks, which can represent at 4p2. Now, lastly, since there are 4 remaining yellow blocks and 1 remaining red blocks, we can represent it as 5p1. This is represented as 2p2 times 5p1 times 4p2 times 5p1. But first, let us solve for 2p2. There is 2 objects taken 2 at a time. In formula form, it is 2 factorial over 2 minus 2 factorial. And 2 factorial will be cancelled, which leaves us with only 2. Now, let us substitute all the values, and when it is substituted, it will look like as 2 times 5 times 12 times 5 times 2, which equals to 1600, and it is 600 for each case. Now, we will add all the answers together, which is 360 plus 600 plus 600, which gets us to 1560 total number of arrangements we can make.
The bridge can be built in 2,160 unique ways. Great job, everyone!
Millie, Gio, I just finished making my 4 supreme, 3 pepperoni, and 2 Hawaiian pizzas. But suddenly, I grabbed in a fit and trapped me. He won't let me go until I tell him how many different ways I can arrange my pizzas. I need your help.
That's a permutation problem. We need to figure out how many different ways you could have arranged the pizzas.
Let us break down the problem. The chef has 9 pizzas in total, which is 4 supreme pizzas, 3 pepperoni pizzas, and 2 Hawaiian pizzas. Since some pizzas are the same, we will use the permutation of identical objects formula. The formula is n factorial over k sub 1 factorial multiplied to k sub 2 factorial multiplied to k sub 3 factorial, where n is the total number of pizza, which is 9, k sub 1 is 4 factorial, which is the supreme pizza, k sub 2 is 3 factorial, which is the pepperoni pizzas, and k sub 3 is 2 factorial, which is the Hawaiian pizzas. Now, we will substitute the values into the formula, which is 9 factorial over 4 factorial multiplied to 3 factorial multiplied to 2 factorial. First, we will find the factorials of each term. The 9 factorial is equals to 362,880. The 4 factorial is equals to 24. The 3 factorial is equals to 6. And the 2 factorial is equals to 2. Now, we will divide it. So 362,880 over 24 multiplied to 6 multiplied to 2 is equals to 362,880 over 288, which will result to 1,260. Wow! That means there are 1,260 different ways that chef could have arranged the pizzas.
Wow! The Hungry Gremlin could have 1,260 different meals. That's a lot of pizza's possibilities.
Thanks, Team Umizoomi. Now I know exactly how many ways I arranged the pizzas.
Pattern power! Problem solve! Umi-rific!
Gio, this doesn't look right. We were supposed to reach Obuena Street, but now we're just going in circles.
Wait a second. This street sign don't even match the map. The permutation monster must have mixed up the signs of the roundabout.
We can use the formula for circular permutation, which is n minus 1 factorial. We just need to substitute n with 7, which will be 7 minus 1 factorial, simplified to 6 factorial, and the final answer would be... That's right! It's 720! There are 720 ways the monster could have arranged the signs.
That means drivers can finally find their way again, including us. Now, we can head straight to Abuena Street.
Great job, Team Umizoomi. We've gathered all the letters we need to defeat the fermentation monster.
Now, we just have to figure out the magic word. What is it based on the letters we collected?
I think I know what it is. I think it's math.
That's it, Gio! Great thinking!
Alright, Team Umizoomi. And you too, Umi friend. Let's say it together and stop the permutation monster once and for all. On the count of 3. 1, 2, 3.
Math!
The city is finally back to normal.
Monsters, but we fix it by solving those problems together.
Great work, Umi friend. You saved Umi City and helped us.
Thank you. Remember, permutation helps us understand arrangements when order matters. Keep practicing, and you'll be a math whiz in no time.
Love, joy, hope.
Oh no! But that turned to a permutation monster!
Great work, Umi friend.
Three, two, one.
Sorry, okay? I'm also panicking! Why are you laughing? Oh no! Bob got turned into a permutation monsters! But we fix it by solving those problems together!
Ayun lang ba yung line mo?
Nga pala to.
Ulit. Shut up! We are the prime dining restaurant!
Fried?
Ulit. Shut up! We are in the...
Hi, ma'am. Welcome. Welcome to our recordings.
Ito yung intro natin. Nakahiga tayo.
Ma'am, nag-sleep over na sila. Happy New Year, ma'am.